most part, our goal here is to explore Python. And to be a little bit more precise about what I mean, to explore how we can make the most precise surgical use of the mechanisms, metaphors, and meaning made available by the design of the Python language in order to solve problems. Behind me, you can see the session page with all of the details about this session. If it is interesting to you to see where this protocol, where this simulator goes, if seeing how we can use other parts of the Python programming language than what we see today is fascinating too, if you want to see the evolution of this program, please sign up for the next two sessions on September 3rd and September 13th. All of these notes will be provided to you after the session is complete. If you are a Backstage Pass holder or a front row seat holder, you'll also get a PDF of these notes and the code repository. And because we're going to go through the theory very quickly, we'll also be providing you with a couple of reference videos. Here you can see my code sharing window, and we'll live code our way through the problem that we're going to take a look at. Our goal with this is to do some sort of modeling problem rather than an analytical problem. And this is a very rough distinction, but you can think an analytical problem might be given some data set, compute some metrics on that data set, some statistics, do some sort of deep learning or other types of machine learning. That might be an analytical problem. A modeling problem, however, is a problem where we take a very complex reality and we try to find the aspects of that reality that can be represented in our code. And we try and find what the correspondences are between this is the business rule or the business domain model, and this is the corresponding Python code that's used in order to implement that. And the reason that we want to build those correspondences, once we begin to see those correspondences, it becomes very easy for us to prototype problems very quickly, and we can write really, really terse and not necessarily everything jammed into one line, but fluent, clear, precise Python. If we are looking to solve a modeling problem, it turns out that distributed algorithms represent a pretty good start for a modeling problem, and simulators even more so. The other part of a simulator and the modeling part of a simulator is we want to figure out, okay, how do we model the things that make this difficult? Well, FLP says it's impossible for you to solve this problem in an asynchronous system where you can have failed nodes. And so that leads us directly to what we're going to do in our simulator. Namely, we're going to try and model different types of failures. Failures like a node hangs for some period of time, but maybe resumes operation, a node crashes. We could even model what are called Byzantine failures. A node, for example, goes nuts and sends messages that are completely nonsensical. And so, let's talk about where our motivation is and how we can tie this problem to Python. Well, we oftentimes see APIs, and in those APIs there's some sequencing of operations. An API that looks like this. You have some operation that you do first, some operation you do second, and some operation you do last. And you can see from this use code here that nothing is constraining us to run these in particular order. Now, if you're struggling a little bit to really picture in your mind what that might look like, think about like a database API where you have to connect and then you have to query and then you close, but you can't really do those out of order. You can't query after you close the connection. You can't close before you connect. There's an in-force sequencing here. Now, if you look at some code like this that's written using an object-oriented formulation, you might wonder, well, is this necessary? Is this object orientation necessary in order for us to implement this sequencing? And you might say, in fact, if I could get away from this formulation, it might be good because this formulation is error-prone. It's not really giving me any guidance for these have to happen in a particular order. Now, before I show you what that guidance might be, consider that the entire reason that we wrote this in an object-oriented formulation in the first place with 3 separate methods was if we had written this all as one method, or did the first, the second, and the last, we could trivially enforce the sequencing. We could trivially enforce the first action happens first, the second action happens second, and the last action happens last. But because Python functions are eager, it would run to completion, and we wouldn't be able to interleave any sort of operations in between. We wouldn't be able to run first and then go off and do something else, and then run the second, then go off and do something else, maybe run the second again, and then run the last. We wouldn't be able to do things in between. And additionally, we wouldn't be able to send data in and out. So we might, for example, take a result from the second operation and then compute some data and send it back in and do the second operation again. In a database query, think, for example, you run some query and then based on that query, you make a decision about whether you want to continue to do queries or you decide which query you want to run. Well, we couldn't do that in a single Big Bang function implementation. We need some way to split this up. Well, it turns out that the Python generator gives us the ability in order to represent